In this lecture, we'll define a function called the conditional probability density function. The starting point is now two random variables that are both continuous and a joint probability density function f of x, y that contains all information about these two random variables. From the joint PDF, I can find the marginal PDF of x and the marginal PDF of y by integrating away one of the variables. The conditional probability density function of y given x is denoted like this, and it's defined as the ratio of the joint PDF to the marginal of x. It's only defined for values of x where this marginal is not equal to 0, but apart from that, it's defined for all other possible values of y and x. We can also do the conditional PDF of x given y, and that function is denoted like this and defined as the ratio of the joint to the marginal of y. In the case of continuous random variables, we know that density functions are not probabilities. So we cannot give this definition an interpretation in terms of probabilities the way we can do when we have discrete random variables. This goes for the conditional PDFs as well. They are not probabilities, but just like joint probability density function and marginal PDFs, we can use them to find probabilities, but we have to do that through an integral as described in just a little bit. Here is a simple example. I have a joint PDF f of x and y, which is equal to x plus y. The range of x is the interval 0, 1, and the range of y is the interval 0, 1. It's not hard to show that the marginal PDF of x is given by 1/2 plus x. All we have to do is to integrate the y variable, 0, 1, f of x, y dy. That comes out to be 1/2 plus x. So the conditional density of y given x is given by this function, which is a function of two variables, x and y. So the question then is, what can we do with conditional PDFs? Well, the answer is we can calculate conditional probabilities, not probabilities such as y equal to y conditionally on x equal to x. Those are pointless when the random variables are continuous because they are all 0. But probabilities that y will end up in an interval when we know the precise value of x, that can be calculated using the conditional density. And we do that simply by integrating the conditional PDF. So if I want to calculate the probability that y ends up in the interval bounded by a and b conditionally on knowing the precise outcome of the x random variable, that is calculated as the integral from a to b of the conditional PDF. Note that we do have an equality for the x random variable, the one we're conditioning on, because even though x is a continuous random variable, when we perform the experiment, x will end up taking a specific real number, lowercase x, and that's the number we use in the conditional probability. So continuing our example, let's say I want to find the probability that y ends up in the interval between 0 and 1/2 conditionally on a specific value of x. Then I integrate y from 0 to 1/2. This is the conditional PDF that we found here, dy. And this integral is equal to 1 plus 4x divided by 4 plus 8x. So the conditional probability that y ends up in this interval depends on the particular value that we observe for x. For example, if I observe that x came out to be precisely 1/4, which of course is a little bit silly, x will not come out to be something as exact as that. Remember, there's an infinite precision in continuous random variables. But then I can just simply take this 1/4 and substitute it in here and here, and then I can calculate an exact probability that y ends up in the interval, and it comes out to be 1/3.